Yeah, draft physics video presentation, something like that. Anyway, I should have these pens over here so they don't make noise. Anyway, sorry about the technical difficulties here and there. Obviously, way too much shadows here, shadowy. But anyway, figure I'll go over this a little bit. This concept of Doppler effect, redshift. And the bits of the conversation, it's still just, it's just not clear as people think it is. It's alright. So the idea is there's this redshift phenomenon happens in these different mediums. So we have the speed of sound, which we know is a transmission through a medium. Now we don't know how light transmits, in the sense that they haven't explicitly proven anything, entirely, whether it's a little particle or whether it's a wave in a medium of some kind of electromagnetic field versus something called an ether, and none of that's been really clearly stated. Now they've clearly stated that they have some evidence that there's no ether thing, but I don't know exactly how an ether would behave different than an electric and a magnetic field. The fields would have to have some sort of structure to be able to transmit waves, and so it's a medium again. So anyway, though, the point being made is that somehow sound does something that light doesn't have the same problem. So there's some sort of mechanical functional thing regarding the transmission of information, or however you want to describe it, these waves. Somehow the ones that are in the form of growing the speed of light, those waves don't have the same problem that sound waves have in terms of an asymmetry or a lack of symmetry in whether the wave is being received or whether it's being emitted, in terms of the effect on what could be called frequency or the period or the wavelength of the stuff. Now, I'd argue if they have evidence, real proof, that sound behaves differently than light, then that would be more evidence that there's no ether, because you could draw the simple conclusion that we know sound has the hard medium of its vibrations of atoms, and we know that that might be the obvious reason why light doesn't have the same problem, is it's not a vibration of some medium, some mechanical structure that's transmitting through movement the energy. But I don't hear those arguments anywhere. I don't hear the argument. I hear the Michelson-Morley argument against ether, but I don't hear well, what about the paradox of the difference between light and sound, in terms of one has asymmetry and one doesn't, and the asymmetry is undone in the electromagnetic circumstance, the light mechanism, because of Einstein's relativity, apparently, which I would argue has to be some sort of mechanical system, and if it exists in that medium, you could have the same kind of thing exist in the other medium. It's just that it would be a much smaller, because of the speed of sound being so much slower. Alright, now I was arguing that I would like to see experimental evidence somewhere, so we haven't got any of that. It seems to me pretty easy to design an experiment. In a sense, I was thinking that you could just spin a speaker and record the sound that it produces as you spin it, rotate it very fast. And and then you could just take that sound that you recorded, reverse it, and play it out the speaker and rotating it again. And technically, it should be exactly undone if there wasn't this problem with transmission versus reception. So that's one experiment. The electromagnetic experiment should be done in the sense that I think the probe they sent to Pluto got up to a pretty high speed, 30,000, 40,000 miles a minute or whatever it was. Really fast. So it would have some Doppler shift in terms of its radio signal it was sending back to Earth, and we should be able to calculate how big that effect is exactly, and know that it's symmetrical in the sense that there's a explicit symmetry between the amount of Doppler shift and the distance traveled in the faster speed. Alright, so that's the context. So Professor Lewin argues that this was a specific phenomenon to sound only, and yet these arguments are arguments that I think can be applied to other circumstances where you can make the same argument about why it has to be asymmetrical in the light example. And all they have is a mathematical fix in the form of the Lorentz transformation. But anyway, I don't want to get into all that crap. So, my fundamental argument is if you look at the experiment in the simplest sense, you have an emitter and a receiver, and the total speed that the two are leaving each other is the speed of sound. So you're essentially doubling whatever's being transmitted between them. You're doubling the space, essentially. So whether you make this going 200 and you make this one going 800, whatever the thing is, your total is, it's 1/3 is what they used in the example, and 2/3 the speed of light for the other one. So the total movement or expansion of this space is you're basically 100%. You're increasing the space by 100%. So whatever's in here, in this space, you're basically just going to double the space in a given amount of time, and in a sense just stretch the stuff in there. So you'll have the same number of bits of information, and you're just basically going to double the distance between them. And that would have to be the consequence of this expansion of the movement, total movement. Now the tricky part is when you analyze the production of the sound, that's where you start to notice this difference, in the sense that you're arguing that the thing producing the sound, in one case can only add space in a specific way, and then the other one that's receiving the sound, the addition of the change in how it's going to receive is dependent on the fact that as it's moving away, it's going to be increasing distance at a different rate. So where this would be doing it at some half rate, this would be doing it at some third rate or something. That the two rates at which one is producing space and at which one is absorbing space are not symmetrical. And I'm doing the short version of their argument because it's just kind of, well, maybe you can, yeah, I don't know. I mean, it just has to do with the fact that if you understand these waves are all moving at the same speed, and then you recognize that when this one gets into this position, this is going to move, away, and that as it moves away, this is going to get to this position where it would have hit it if it was still there, but it moved away, and the time it takes it to make up this little bit of extra distance, this is going to move away a little bit more and away a little bit more, and so there's this incremental increase that turns out to be something more or less than just a clean doubling of the frequency. See, I would argue that in the case of you're just making twice as much distance, you could just assume that half the distance is created at the emitter and half the distance is created at the receiver. Alright, so what I was thinking about was the fact that what those examples don't take into account is the fact that the thing emits sound in a specific way. So this goes to my argument that sound is created by something essentially breaking the sound barrier. So every sound you hear is made of little sonic booms. So, when my voice makes sound, or when a stupid phone makes sound, it's making the sound, stop it, it's making the sound by moving something material faster than the speed of sound. So it creates little, and the intensity of the sonic boom is based on the fact of how much matter you're moving. So the classic example is the tip of a whip. You know, that the whip curls, you know, folds over itself, and as you straighten the whip, there's leverage in the folds, and as the folds unfold, the tip of the whip actually breaks the sound barrier, and that's the crack you hear, is the crack sound of the whip, the tip of the whip, moving faster than the speed of sound. Well, I'd argue that everything is functioning that way. So when something creates sound, it's creating it by creating movement. And so the trick is that when you're thinking about the object creating sound, you can't think of it as just some static thing that just creates sound. It's actually sort of like, you have to sort of think of it as like it has a pendulum inside of it, let's say, you know, that's going back and forth. And that as the object moves backwards, if the pendulum's also moving backwards, it's as if the pendulum isn't moving. You know, you can sort of understand that if you give the clock motion in the direction that the pendulum's moving, the pendulum will stop moving, essentially. And so there'll be no, it won't do its, it won't swing properly, you know, because you're moving its frame and essentially time dilating it in a sense. And that's part of the creation of the vibration, is the fact that to create sound you essentially have to have a vibration. That is, something has to recharge and then release the charge. It has to recharge and then release the charge. It has to you know, it has to go in one direction to go in the other direction. It can't possibly just go forward, go forward, go forward, go forward to make sound if it's stationary. Your speaker doesn't start moving towards you as it makes sound. It obviously is retracting and then moving forward, and then retracting and then moving forward to make sound. And so that's the complication in the theory, is you have to recognize that as the sound's being created, there's a mechanism creating the sound, and the mechanism creating the sound is being affected by the motion. So this sort of relates to my argument about time dilation, in the sense of, you know, in the Einstein sense, that time dilation isn't a reflection of time being bent. It's a reflection of the fact that when you move matter, you'll change its function, and things like atomic decay will happen at a different rate because you're changing the mechanics of the atoms. As you move them through space, you're changing the orbital speed depending on what state they were in when you moved them. So let's see, how's the pendulum is kind of a decent example. I'm just saying, is if the pendulum is swinging this way and you move the whole frame as the pendulum's swinging, the pendulum's still moving, but the motion becomes invisible because the frame is moving with the motion. And you know, that's sort of going to slow down the retraction of the spring. And so in a sense it changes the frequency of the swing of the pendulum. You're changing the period of the pendulum. If you move the frame that the pendulum's swinging in, you'll change the period of the pendulum. And you know, that's the mechanism that's counteracting against the asymmetry between the emitter and the receiver. So the emitter, this is going to mean something, this whole vibration thing. The fact that you're moving something that's vibrating, which means you're sometimes moving it in the direction of its recharge, so it doesn't recharge. The recharge takes longer. But you're moving it slower than the recharge speed, but I'm saying it takes longer for the pendulum to swing because you're moving the frame. Now on the opposite end, the receiving end, it doesn't matter, because the receiving surface, all right, it doesn't matter how the pendulum moves, it's still going to be received. So the fact that it's off sync, okay, with the vibration that would happen, because the vibration is coming from the outside, recharging doesn't matter. You're not moving a pendulum, so to speak, in terms of creating a frequency. You don't have to do the rebound thing. You're just hitting a surface, and the surface is creating a reaction. So there's no counter effect on the other side. So it's really just undoing the difference in the effects of the two sides is only being undone by the emitter side, because it was only the emitter side that was inaccurately representing the frequency, or inaccurately creating its share of the frequency. Now this still doesn't explain Professor Lewin's numbers, where he came up with 250 and 400. So we had a total, we started with 100 hertz, and then somehow we had and we moved a total of one speed of sound. You know, we doubled the speed of sound. We doubled the distance. So we doubled the distance, or you could say we had to double the wavelength in a sense in total. And yet the difference in the frequency was numbers of 250 and 400, and clearly that doesn't average out to 500. You know, because 500 hertz is what we're supposed to end up with. You know, if you change from this distance and you have 10 lines in between there, and then you expand the ruler by 2, you know, just double it, and you still have 10 notches, you have every expectation those notches have to be twice as big. And in this case, the wavelength, it would be twice as big a wavelength means half as much hertz. And so these numbers don't, I can't see how you make those two numbers come out to 500 hertz. So it still lacks symmetry if those numbers were real. So I just don't think those are accurate. That if you were going to have a disproportion, the disproportion would have to be like 200 and 300, because it would somehow still have to average out to 500 in the end in terms of the total effect. Would still have to get you to 500 hertz. So I really don't understand how to fix that problem with this explanation if those numbers are accurate. But you know, I suspect that neither one of those numbers is an accurate reflection of the effect on the total system. So that's sort of where where we're stuck. But I'm just saying that, you know, there's lots of subtleties to any one of these experiments in the terms of you can't make assumptions too vague an assumption about the mechanical functions. And so it's a lot like when Hathaway talks about reflections, and when a lot of people talk about reflections. I mean, do we really have the expectation that a photon, when it reflects, just hits some magical thing and then bounces off? You know, it just hits a surface of some kind, something called surface. Or do we understand that the photon has to interact with an electron, that the electron is going to move, that something's going to happen to the photon in that process in the sense that it might change its momentum, and that this interaction is going to have to be more complicated than just saying it bounces off. It doesn't just bounce off. It, in a sense, becomes part of the surface that it hits, and then the surface, you know, the energy goes through the material and in a sense comes back out of the material, and that there's a real event there. It's not, it spends time inside the surface. It is essentially, as stated, it's like the baseball example in the sense that the baseball doesn't bounce off our hands. We don't just put our hand out, the baseball bounces off. We catch the ball, and then when we re-release it, it's going to have our momentum built into it, in the sense that if we have some other motion, the baseball is going to have built into that a new vector, a new direction. There's not going to be any free exchange where it just bounces off of us for free. And I've sort of pointed out that in my explanation, this is probably a U-turn, is essentially what is really happening when photons go in. that their angle is likely incorporated into some this idea of this perpendicular thing, and the idea that if you have two of those perpendiculars, you'll end up with a U-turn, two right turns, and you'll come out the same angle that you went in. So depending on how you interact with the surface will dictate how you exit the material, essentially. So something going in straight in will end up going straight out. Something that goes in on an angle will end up having its angle recorded, in the sense that it'll take 3 right turns to create that same angle. 3 right turns? Well, no, he only needs 1 right turn. In that case, right? Yeah. So in a sense, no matter what angle it came in this way, well, the angle has to represent, it has to be this angle, so it can't be just a perpendicular. So yeah, it takes 3 interactions to create the reaction. Yeah, I don't want, that's sort of a separate subject, so I don't want to get into it too deep. But I'm just saying, I would argue that there's no such thing as just some sort of bounce off the surface. It's always interact with the surface, absorbed by the surface, and then the surface says we can't hold that energy, and it re-releases it because it has no mechanism to retain it. So it goes in, wobbles about, and then the system says we can't hold it, and it releases it. Alright, that's probably enough for the purpose of this video. So the major points are, do we have any physical evidence demonstrating this phenomenon with sound? And I don't see it yet. The difference between the fact that this effect doesn't happen with radio waves in terms of the disproportional symmetry should be pretty provable, in the sense that we do have evidence of satellites and whatnot, and we should know this for sure about Doppler effect if it's completely proportional to the speed. Like if you went half the speed of light, you would create 1/4 of no, you'd create half a half wavelength change in the wavelength. And if you went the speed of light, you would create a doubling of the wavelength if it was possible. What was the other bit? Yeah, so we don't, the physical evidence is weak, and I would say just on its face, logically, it's very hard to rationalize these proportional numbers with just the absolute case of recognizing that 1/3 the speed of sound plus 2/3 the speed of sound has to equal, as a total distance, a doubling of the wavelength. And I don't know how you can get around that as just a physical fact. Okay. And then, of course, the more complex part of the argument having to do with the fact that anything that's creating sound is doing it by moving, and that motion has to also be accounted for, and you're moving at the speed of sound, or faster. That's the whole way you're creating sound, is by moving faster than the speed of sound. And that motion is, it's as if the pendulum's moving faster than the frame motion. So I'm just trying to reiterate that the frame's moving at say 3/4 the speed of sound, or just 2/3 the speed of sound, or 1/3 in the example. But obviously the thing that's actually emitting the frequency has to be moving faster than the speed of sound to create the waves that are sound, the vibrations in the atoms. Yeah, and it's the disproportional between those two speeds that is creating a lengthening of the period. Okay, so enough. Yeah, I'd like it to be simpler, to say that, some simple way to say that, but there is a mechanical process. So all I'd like you to accept is the idea that yes, you can understand if a pendulum's swinging and I move the box the pendulum swinging in, that it's going to appear as if the pendulum is swinging irregularly. Okay. So, until next time.